On July 21, 2025, the Hubble Space Telescope turned its gaze toward a point in space 277 million miles from Earth and caught something that should not have mattered to anyone but a handful of comet specialists. A teardrop of dust and ice. A hyperbolic trajectory. An object passing through our solar system exactly once in all of human history. Its designation: 3 Atlas, the third confirmed interstellar visitor. A wanderer from the dark between stars. Since that first image, every new orbit solution, every brightness spike, every sideways twist in its plasma tail has been quietly stitched into a single file on a few overworked servers. The data grows, the patterns deepen, and the questions multiply faster than the answers. In June 2025, the Vera C. Rubin Observatory opened its eyes for the first time and began sweeping the southern sky with a camera large enough to fill a room, promising to catch anything that moved, from faint galaxies billions of light-years away to wandering ice just beyond Mars. In November 2025, ESA's JUICE spacecraft turned its sensors toward 3 Atlas, catching early glimpses of a glowing coma and tangled plasma and dust tails. The kind of complexity you don't expect from a simple piece of frozen rock drifting between the twin stars. Then just days ago, a new trajectory update quietly dropped into the public databases. The numbers moved by millimeters per second and fractions of a degree. But they changed everything about how close 3 Atlas will come, how long we can see it, and how many instruments will still be alive when it crosses the plane of our solar system. At the same time, a NASA-led study warned that a sky crowded with satellites could contaminate up to 96% of images from some upcoming space telescopes, threatening the very data we need most. Budgets are under pressure. Missions are delayed. Teams are being asked to do more with less. And somewhere out there, an interstellar comet is threading a path through that shrinking observational window with unnerving precision. One anomaly stands out above all others. In the latest JUICE and Hubble data, the plasma tail of 3 Atlas doesn't just point away from the sun. It kinks. It leans. It seems to follow slight shifts in the solar wind in a way that hints at magnetic structures, or jets that turn on and off in a pattern we still don't understand. The odds of an interstellar object with these exact properties threading this specific corridor through our inner solar system by random chance have been calculated at roughly 1 in 20,000. Some call it statistical cherry picking. Others argue that when coincidences start stacking, unlikely stops being a comfort. Before we go further, hit like, subscribe, and tell me where you're listening from, because this story is still unfolding, and you're part of the network of eyes watching it happen. That's where this chapter of the story begins, with a new trajectory update that behaves less like a random visitor from deep space, and more like a message written in motion. This is not science fiction. This is December 2025. Chapter 1. June 23, 2025. First light over Cerro Pajon. The air over Cerro Pajon in northern Chile is thin and cold, the kind of cold that clarifies everything it touches. At an altitude of 8,800 feet, the sky is darker than most people will ever see with their naked eyes. And on the night of June 23, 2025, that darkness was about to become the most valuable real estate in astronomy. Inside the dome of the Vera C. Rubin Observatory, a camera the size of a small car, powered on for the first time in full survey mode. Not a test. Not a calibration run. First light. The camera's focal plane is a mosaic of 189 charged coupled device sensors, arranged in a grid so precise that the tolerance between adjacent chips is measured in microns. Together, they form a 3.2 gigapixel eye capable of capturing an area of sky equivalent to 40 full moons in a single exposure. The field of view is so wide that it takes roughly 400 ultra-high-definition screens, arranged side by side, to display a single frame at native resolution. Engineers in the control room watched their monitors as the first image began to populate, line by line, a cascade of stars flooding onto the screen like rain hitting pavement. "This is it," someone said quietly, though no one was sure who. "The southern sky is dense. The Milky Way cuts through it like a scar of light, and beneath that bright band lie billions of stars, tens of thousands of galaxies, and uncounted objects moving through the dark, asteroids, comets, distant Kuiper belt bodies, and perhaps, if you're lucky or unlucky enough to be looking at the right moment, something from beyond. Rubin's mission is deceptively simple. Scan the entire visible sky every few nights, over and over, for 10 years. Watch for anything that moves, changes, or appears where nothing was before. It is designed to be the heartbeat of the night, a metronome of detection that will quietly define what we notice and what we miss. Within hours of that first full survey image, processing pipelines began chewing through the data, comparing new frames to older reference images taken during commissioning. They flagged transient events, supernovae blooming in distant galaxies, asteroids crossing between exposures, variable stars pulsing in predictable rhythms. And then, buried in one subset of the data, the software tagged a faint, fast-moving point. Not an asteroid. The motion was too smooth, too directed. Not a satellite. The trajectory didn't fit any known orbital path. Just a point, streaking across several frames at a velocity that suggested it was far beyond the orbit of Mars. Perhaps beyond Jupiter, moving with a purpose that seemed almost deliberate. At the time, no one connected it to 3 Atlas. The comet hadn't been formally designated yet. It was just another faint smudge in a sky crowded with faint smudges. One more entry in a list that would grow by tens of thousands over the coming weeks. But later, when teams began backtracking through Rubin's early data, they would find that point again, and they would realize it had been there all along, moving through the exact corridor where 3 Atlas was headed, as if the universe had marked the path weeks before anyone knew to look. Inside the control room, the mood was celebratory. Champagne bottles were opened, non-alcoholic, because there were still systems to monitor, and someone projected the first full-field image onto the largest screen, a tapestry of light so dense that it looked less like a photograph and more like a living map of infinity. "Welcome to the new era," the lead scientist said, raising a plastic cup toward the screen. No one in that room knew what was coming. No one suspected that the very sky they were celebrating, the sky they would scan night after night with unprecedented precision, was already shifting under the weight of 10,000 satellites, already fragmenting into observational windows that would close faster than mission planners had anticipated. And no one guessed that within weeks, an interstellar comet would begin threading a path through those windows with a precision that would haunt every attempt to reconstruct its full trajectory. The Rubin Observatory was designed to see everything, but everything is a moving target. And some things, it turns out, know exactly where the gaps are. As the celebration wound down, and the engineers returned to their stations, the telescope tilted toward a new patch of sky. Its massive mirror gathered starlight from a region just above the plane of the ecliptic, a region that, according to the schedule, would be revisited in 3 nights. But by then, the object in question would have moved. Not by much, just enough. Just enough to require another observation, another fit, another iteration of uncertainty. 3 weeks later, when Rubin entered its planned engineering hiatus, teams would look back at those early June images and realize they had captured the best continuous coverage of 3 Atlas's inbound trajectory. Everything after that would be fragments, pieces of a puzzle scattered across institutions, instruments, and international borders. Cerro Pajon is remote. The nearest major city is over 100 miles away, and on clear nights, the only light pollution comes from the instruments themselves, red LEDs glowing faintly inside the dome. On June 23, 2025, the sky above that mountain was as dark as it had been for 1,000 years. But the sky was speaking. And whether anyone was ready to listen or not, the message had already begun. 3I. Atlas doesn't slow down while we decide what to believe. Chapter 2, July 21, 2025. A hyperbolic stranger enters frame. There is a particular quality to Hubble images that no other instrument quite replicates. It's not just the resolution, though at 0.05 arcseconds per pixel, Hubble can resolve details smaller than a dime seen from 2 miles away. It's the way the telescope holds its gaze, steady and unwavering, locked onto a single point in space while the Earth spins beneath it. On July 21, 2025, that gaze settled on 3A Atlas. The observation was scheduled weeks in advance, part of a director's discretionary time allocation requested by a consortium of comet scientists who had been tracking preliminary reports of an inbound object with an unusual orbital solution. The target was faint, magnitude 22 in visible light, barely brighter than the faintest stars Hubble can detect, but the tracking data from ground-based surveys suggested it was worth the effort. Hubble's Wide-Field Camera 3 captured a series of exposures over the course of 2 orbits, roughly 3 hours of observing time spread across a single night. Each exposure was 90 seconds long, just enough to gather light without saturating the brightest background stars. When the images came down and the processing pipeline stitched them together, something remarkable appeared. Not a point, but a teardrop. A diffuse coma of gas and dust, glowing faintly in reflected sunlight, stretched into a thin tail that streaked across the frame. Background stars, sharp and static, provided the reference grid, and against them, the comet moved, streaking, blurring, carving a line through the frame like a brushstroke on black canvas. It was beautiful, and it was hyperbolic. The orbital solution had been refined 3 times in the week leading up to the Hubble observation, each iteration folding in new astrometry from automated surveys. The eccentricity of the orbit was now pinned at 1.032, meaning the comet's trajectory was not a closed ellipse, but an open curve, a path that entered our solar system from interstellar space, and would, barring any significant perturbations, exit into interstellar space again. It was only the 3rd time in recorded history that such an object had been confirmed. The first, Oumuamua, arrived in 2017, a dark, elongated body that tumbled end over end and accelerated away from the sun, faster than gravity alone could explain. It sparked years of debate, ranging from mundane outgassing to more speculative ideas involving light sails and ancient probes. The second, Tuiwai Borisov, arrived in 2019, a more conventional comet with a visible coma and a composition that closely matched objects born in our own solar system. It was strange, only in its origin. Everything else about it was comfortingly familiar. 3. Atlas was different. The coma was larger than expected for an object at this distance. At 277 million miles from Earth and roughly 320 million miles from the Sun, it should have been barely active, its ices still locked in deep freeze. Yet the Hubble images clearly showed a cloud of material extending more than 10,000 kilometers from the nucleus, backlit by sunlight and glowing faintly in the ultraviolet. The tail was even stranger. Most comets have 2 tails, a dust tail, broad and curved, pushed by the pressure of sunlight, and a plasma tail, narrow and straight, sculpted by the solar wind. 3 Atlas had both, but the plasma tail didn't behave the way it should. It pointed generally away from the sun as expected, but it kinked, bent at a shallow angle, as if something had nudged it sideways. One team member, reviewing the images in a late-night Zoom call, zoomed in on the kink and stared at it for a long time. "That's weird," she said finally. "Weird how?" someone asked. "Weird like I don't know what would do that." The conversation moved on. There were deadlines, proposals, other targets to discuss, but that comment lingered in the back of everyone's mind. Over the next 2 weeks, ground-based observatories continued tracking 3 Atlas, and each new set of measurements tightened the orbit solution. The velocity at infinity, the speed the comet would have if it escaped the sun's gravity entirely, was calculated at 6.2 kilometers per second. Fast, but not impossibly so. Consistent with an object that had been wandering the galaxy for millions of years before stumbling into our neighborhood. But there was a problem. When orbital dynamicists tried to fit the data using only gravitational forces, the sun, the planets, the usual perturbations, the model didn't quite work. There were residuals, tiny mismatches between where the comet should be and where it actually was. Non-gravitational accelerations. Every active comet experiences them. As the nucleus heats up, ices sublimate, jets of gas erupt from the surface, and those jets exert a force, tiny but measurable, that nudges the comet slightly off its purely gravitational path. For most comets, these accelerations are straightforward. They point roughly opposite the sun, scaling with solar heating, and they decay predictably as the comet moves away. For 3I Atlas, they didn't quite fit that pattern. The accelerations were there, clearly present in the data, but their magnitude and direction seemed to vary in ways that didn't align with the expected solar heating profile. Some observations suggested the comet was accelerating slightly toward the sun, others away, and still others tangentially, as if it were course-correcting in mid-flight. At a working group meeting in late July, one dynamicist presented a slide showing the residuals, observed position minus predicted position, plotted over time. The scatter was small, just a few arcseconds, but it wasn't random. There was structure. Noise in the fit, someone suggested. Maybe, the presenter replied. Or maybe the outgassing isn't symmetric. Maybe there are multiple jets firing at different times. Or maybe, someone else added, half joking, it has an engine. The room laughed, but not for long. Because the truth was, no one could rule it out entirely. Not yet. The non-gravitational forces on Oumuamua had sparked similar speculation. Some scientists argued they proved the object was natural, just a comet with a symmetric outgassing. Others pointed out that the accelerations were oddly consistent with what you'd expect from a damaged light sail or a derelict spacecraft venting propellant. In the end, the jury was still out. And now, here was 3A Atlas, exhibiting its own set of tiny, inexplicable adjustments, just enough to keep the orbit solution uncertain, just enough to require more observations, more refinement, more time. Time that, as it turned out, no one had as much of as they thought. On July 28th, a week after the Hubble images were released, a grad student at a small university in Europe ran a quick statistical test. She took the orbital parameters of 3I Atlas and compared them to a Monte Carlo simulation of 10 million randomly generated hyperbolic trajectories, checking how many would pass within the inner solar system during this particular observing season, with this particular geometry visible to this particular set of observatories. The result came back as a probability, roughly 1 in 300. Not impossible, but not common. She filed the result in a shared folder and went back to her thesis work. But someone else saw the file, and quietly, without fanfare, they began to wonder if 1 in 300 was close enough to unlikely to be worth paying attention to. 3I Atlas doesn't slow down while we decide what to believe. Chapter 3, August 9th, 2025. The Tale That Forgot the Sun. By early August, 3 Atlas had become a minor celebrity in the small, passionate world of comet science. Observation requests poured in from facilities around the globe, ground-based telescopes in Chile, Hawaii, South Africa, and Australia, space-based instruments like Hubble and the James Webb Space Telescope. Even amateur astronomers with backyard setups sophisticated enough to capture faint objects in long exposures. The data began to accumulate, and with it, the mystery deepened. On August 9th, a coordinated observing campaign brought together 5 observatories across 4 continents, synchronized to capture 3I Atlas over the course of a single night. The goal was simple: track the comet continuously, image by image, to build a time-lapse sequence showing how the coma and tails evolved in near real time. The resulting dataset was stunning. Each observatory captured the comet in a slightly different wavelength: visible light, near infrared, ultraviolet, and when the images were aligned and color-coded, the structure of 3 Atlas revealed itself in exquisite detail. The dust tail was broad and diffuse, curving gently as particles of different sizes were pushed by sunlight at different rates. The smallest grains, barely larger than smoke particles, formed a faint, straight spike pointing almost directly away from the sun. Larger grains lagged behind, creating a fan-shaped arc that traced the comet's recent path. But it was the plasma tail that stole the show. Plasma tails are made of ionized gas, molecules stripped of their electrons by ultraviolet light from the sun, then caught and dragged along by the solar wind, a constant stream of charged particles blowing outward from the sun's corona at 1,000,000 miles per hour. In most comets, the plasma tail points directly away from the sun, like a windsock in a steady breeze. It's one of the most reliable features in all of comet science, so reliable that deviations are almost always attributed to turbulence in the solar wind, localized gusts and eddies that momentarily push the tail off axis before it snaps back into alignment. 3. Atlas's plasma tail didn't follow that script. In the time-lapse sequence, compiled from images taken over 8 hours, the plasma tail could be seen bending. Not smoothly, not gradually, but in a distinct kink roughly a third of the way along its length, as if an invisible hand had reached out and nudged it sideways. The kink persisted for nearly 3 hours. Then, between one frame and the next, it straightened. And then, faintly, it began to bend again, in the opposite direction. One of the lead observers, a veteran comet scientist who had tracked dozens of objects over a 30-year career, watched the animation loop on her screen and shook her head slowly. "I've never seen that before," she said. Her colleague, sitting across the table with a laptop full of solar wind data, nodded. There was a stream interaction that night. The solar wind speed jumped from about 400 kilometers per second to nearly 600. That could explain the first kink. When did he? Could it explain the second? He pulled up a plot. Not really. The wind stayed fast and steady after that. There's no obvious trigger for a second deflection. They sat in silence for a moment, staring at the looping animation. "What if the comet is doing it?" she asked finally. "Doing what?" "Pushing the tail, jets firing asymmetrically, creating localized pressure differences in the coma that interact with the solar wind." It was a reasonable hypothesis. Comets are not passive objects. They're dynamic, chaotic, constantly venting gas and dust in ways that depend on their rotation, their composition, the angle of sunlight hitting their surface. A well-placed jet, firing tangentially to the tail, could in theory nudge the plasma sideways. But that would require a very specific geometry and a very specific timing. And it would raise the question, why would a comet do that? Over the following week, 3 independent modeling groups took a crack at simulating the plasma tail behavior. They used magneto-hydrodynamic codes, numerical simulations that solve the equations governing how ionized gas moves through magnetic fields, and they fed in the observed solar wind conditions, along with educated guesses about the comet's rotation and outgassing rate. The first group produced a simulation that captured the broad structure of the tail, but missed the kinks entirely. The second group got closer, reproducing a single deflection by adding a rotating jet on the nucleus that fired every 12 hours. But their model predicted the tail would spiral, not kink and straighten. The third group tried something different. They didn't assume the comet was rotating uniformly. Instead, they allowed the rotation axis to wobble slightly, and they added multiple jets, 3 or 4, firing in sequence, each one time to interact with the solar wind at a specific phase of the wobble. The result was uncanny. The simulated tail kinked, straightened, and kinked again, almost exactly matching the observed sequence. "Beautiful," one of the researchers said when the animation finished rendering. "Too beautiful," another replied. Because here was the problem. The wobble they had to assume, the timing of the jets, the alignment of the rotation axis, all of it was so finely tuned that it felt less like a natural outcome and more like something engineered. Not impossible, just precise. The team sat on their results for 2 days, running sensitivity tests, tweaking parameters, trying to break the fit. They couldn't. Every time they relaxed one constraint, they had to tighten another. The model worked, but only if everything was just right. Finally, they submitted a preprint to the arXiv, a public repository for scientific papers awaiting peer review. The abstract was carefully worded. "We present a multi-jet model that successfully reproduces the observed plasma tail morphology of 3 Atlas. While this model is consistent with natural outgassing processes, the required parameter values suggest a high degree of structural complexity within the nucleus." In the acknowledgments, buried at the end, they added a single line. "We cannot, at this time, rule out alternative explanation." It was the closest a peer-reviewed paper could come to saying, this might not be natural. The preprint was posted on August 16th. By August 17th, it had been downloaded more than 10,000 times. By August 18th, it was trending on social media. And by August 19th, the first speculative articles began appearing. Is 3 Atlas a comet or a probe? The scientists involved issued a joint statement, emphasizing that their model was one of many possible explanations, that natural processes were still the most likely cause, and that extraordinary claims required extraordinary evidence. But the genie was out of the bottle. People were paying attention now. And in the control rooms of observatories around the world, schedulers were quietly bumping 3I Atlas higher on their priority lists, clearing time, rearranging plans, making room for something that might, just might, be more than a comet. The tail that forgot the sun had become the tail that couldn't be ignored. And somewhere, threading its way through the dark, 3I Atlas continued on its hyperbolic path, its plasma tail trailing behind it like a flag in a wind no one fully understood. 3. Atlas doesn't slow down while we decide what to believe. Chapter 4, September 21st, 2025. The Rubin Gap. The Vera C. Rubin Observatory was designed to be relentless. Its mission timeline, laid out in planning documents years before first light, called for continuous sky surveys night after night, weather permitting, for an entire decade. The goal was to build a living map of the sky, updated every few days, tracking everything that moved or changed with unprecedented completeness. But even the most relentless machine needs maintenance. On September 21st, 2025, Rubin entered a planned engineering hiatus. The official announcement, posted to the project's public website, was technical and brief. On-sky commissioning activities will pause for approximately 4 weeks to allow critical upgrades to the camera cooling system and telescope controlling system and telescope control software. Observations are expected to resume in late October. To most of the world it was routine, just another engineering milestone in a complex, multi-year project. To the teams tracking 3I Atlas, it was a disaster. The timing could not have been worse. In late September, 3E Atlas was entering its peak visibility window, brightening rapidly as it approached the inner solar system. Ground-based surveys like Pan-STARRS and Atlas, the same automated system that had discovered the comet months earlier, were tracking it nightly, but their fields of view were relatively narrow, and their cadence was limited by telescope time shared with other projects. Rubin was different. Rubin's wide-field camera could capture the entire region of sky around 3I Atlas in a single exposure, and its rapid cadence meant it could revisit that region every few nights, building a continuous timeline of activity. For an object as dynamic as a comet, especially one exhibiting the kind of non-gravitational accelerations and tail morphology that 3 Atlas was showing, that kind of dense, uniform coverage was invaluable. It was also, as it turned out, irreplaceable. Inside, a Slack channel shared by several observatories, the tone shifted from cautious optimism to quiet frustration. 4 weeks? Someone typed. We're going to lose the best month. Can we get additional time on Gemini or Subaru? Another asked. Already requested. Both are oversubscribed. Maybe a few nights if we're lucky. What about space assets? Hubble is booked solid. Webb has a packed schedule. JUICE is good, but it's not a survey instrument. So we're flying blind. There was a long pause in the channel, the kind of silence that speaks louder than words. Finally, someone posted a link to a plot, a timeline showing the predicted brightness of 3I Atlas over the next 6 months, with shaded regions indicating when major observatories would be pointed at it. There was a gap, a dark band stretching from late September through most of October, where no survey-class telescope would have continuous coverage. The Rubin Gap. It wasn't absolute. There would still be observations, snapshots captured by smaller instruments, spectroscopy from large telescopes, data from spacecraft like JUICE. But it wouldn't be the same. The continuity would be broken. The timeline would fragment. And for an object whose behavior depended on subtle changes over time, that fragmentation could mean missing the most critical data entirely. One team led, sitting in her office late at night, staring at the gap on her screen, thought about what might happen during those 4 weeks. What if 3I Atlas brightened unexpectedly? What if the plasma tail kinked again, or spiraled, Or did something entirely new? What if the non-gravitational forces spiked, or vanished, or reversed direction? What if the comet was trying to tell us something, and we missed it because we weren't looking? She opened a new document and started drafting an email to the Rubin Project office, making the case for cutting the hiatus short, prioritizing sky coverage over software upgrades, anything to keep the telescope online. Halfway through, she stopped. She knew the answer before she even sent it. The camera cooling system wasn't optional. Without it, the sensors would overheat, noise would swamp faint signals, and the data quality would degrade to the point of uselessness. The software upgrades weren't optional either. There were bugs in the telescope control system that occasionally caused tracking errors, small misalignments that added up over time and corrupted astrometry. The hiatus was necessary. And 3i Atlas didn't care. She deleted the email and closed her laptop. Elsewhere, other teams were running calculations, trying to determine how much they could infer from sparse data. If they had observations before the gap and after the gap, could they interpolate what happened in between? Could they model the missing weeks and test whether the comet's behavior was consistent with a smooth, predictable evolution, or whether something had changed? The answer, mathematically, was maybe. But maybe is not a comfortable place to be when you're trying to reconstruct the trajectory of an interstellar visitor whose path already looks suspiciously non-random. On September 28th, exactly 1 week into the hiatus, a magnitude 7.2 earthquake struck off the coast of northern Chile. No one was injured. The Rubin Observatory, built to withstand seismic events, rode out the shaking with barely a scratch. But the quake triggered automatic safety protocols, requiring a full structural inspection before operations could resume. The inspection took 3 days. The 4-week hiatus became 4.5, and the gap widened. In the final week of September, an amateur astronomer in New Zealand, working with a 14-inch telescope and a homemade CCD camera, managed to capture a single image of 3 Atlas. The comet was faint, just at the edge of detectability, and the image was noisy, but it was there. He posted the image to an online forum dedicated to comet observers, along with the timestamp and coordinates. Within hours, someone had cross-referenced it with earlier observations and noticed something odd. The comet was slightly ahead of where the orbit solution predicted it should be. Not by much. Just a few arcseconds. But it was another residual, another tiny mismatch, another hint that 3 Atlas was not quite following the script. And there was no one, no survey telescope, no coordinated campaign, in position to follow up. The Rubin gap wasn't just a hole in the data. It was a blind spot in time, a stretch of weeks where the most capable sky survey ever built was silent, and an interstellar comet slipped through the dark just beyond the reach of our best instruments. Later, when teams reconstructed the full timeline, they would mark that gap with a different shade on their plots. Not black, but gray, a region of uncertainty where the data was too sparse to say anything definitive. And they would wonder, quietly, whether the comet had known, whether it had threaded its path through our observational windows with just enough precision to be noticed, but never fully seen. 3 Atlas doesn't slow down while we decide what to believe. Chapter 5. October 13th, 2025. Starship points at the visitor. On the morning of October 13th, 2025, SpaceX's Starship Flight 11 lifted off from the Boca Chica launch site in South Texas, under a sky so clear it looked artificial. The rocket was impossibly large, nearly 400 feet tall, stacked in 2 stages, the most powerful launch vehicle ever flown. Its 33 Raptor engines ignited in a carefully sequenced cascade, each one a controlled explosion of liquid methane and liquid oxygen, and together they produced a roar that could be heard 50 miles away. Starship cleared the tower, pitched over, and began its arc toward space. 3 minutes later, the Super Heavy booster separated, flipped, and began its descent, firing 13 engines in a suicide burn that slowed it to a walking pace just meters above the ground. Mechanical arms, chopsticks, in SpaceX parlance, caught the booster mid-air, plucking it from the sky and setting it gently onto the launch mount. 8 minutes after that, the Starship upper stage re-entered the atmosphere over the Indian Ocean, plasma streaming past its heat tiles, and splashed down intact, floating upright in the water, until recovery ships arrived. It was the 11th test flight, and it was perfect. Inside Mission Control, engineers watched the telemetry streams and allowed themselves a rare moment of satisfaction. Starship was no longer a wild experiment. It was becoming operational. And that changed everything. For years, Starship had been the promise of cheap, reusable access to space. A vehicle that could carry 100 tons to low Earth orbit, refuel in space, and continue on to the Moon, Mars, or beyond. But promises are fragile, and the gap between concept and reality is littered with failed prototypes and overrun budgets. Flight 11 closed that gap. Within hours of the successful landing, internal memos began circulating at NASA, ESA, and several private aerospace companies. One memo, sent from a small working group at NASA's Jet Propulsion Laboratory, carried the subject line, Rapid Intercept Feasibility, 3 Atlas. The document was short, just 3 pages, but it laid out a scenario that, weeks earlier, would have been dismissed as science fiction. Starship's payload capacity, combined with its ability to refuel in orbit, meant it could theoretically carry a small swarm of probes deep into the solar system on a trajectory fast enough to catch 3 Atlas before it left the inner solar system entirely. The concept was simple in principle. Launch a stripped-down Starship upper stage into low Earth orbit, refuel it with multiple tanker flights, then fire the engines in a single high-energy burn that would send the vehicle and its payload on ANT's payload intercept course. The payload itself would be minimal, a cluster of small spacecraft, each no larger than a washing machine, equipped with cameras, spectrometers, magnetometers, and dust collectors. They would separate from Starship weeks before the intercept, spreading out into a loose formation, and fly through the coma of 3 Atlas at a combined velocity of more than 50 kilometers per second. It would be a one-way trip. There would be no time to break, no chance to orbit, no possibility of sample return. The probes would hurtle through the comet's tail, gather data for a few minutes, and then continue on into interstellar space, their transmitters fading as they drifted beyond the reach of Earth's antennas. But those few minutes could be enough. Enough to measure the chemical composition of the coma with precision. Enough to map the magnetic field structure around the nucleus. Enough to image the jets, if they were real, and determine whether their behavior was consistent with natural outgassing or something more controlled. The memo included a preliminary delta-V budget, a mass estimate, and a rough cost projection. Approximately $1 billion, assuming Starship launch costs continued to fall as reusability improved. It also included a launch window. They had 60 days. Maybe 70, if they pushed the intercept deeper into the outer solar system, sacrificing data quality for a few extra weeks of prep time. After that, 3I Atlas would be too far, too faint, and moving too fast for any realistic intercept mission. The memo circulated quietly. No press release. No public announcement. Just a handful of decision-makers, reading and rereading the same 3 pages, weighing the engineering challenges against the scientific opportunity, the cost against the potential return, the risk of failure against the risk of doing nothing. At NASA, the response was measured. The agency was already under budget pressure, stretched thin by commitments to the Artemis lunar program, the Mars sample return mission, and a dozen other priorities. Adding $1 billion comet intercept, especially one targeting an object that might be nothing more than an unusually active comet, was a hard sell. At ESA, the reaction was cautious but interested. Europe had a history of comet missions, Giotto, Rosetta, JUICE, and the idea of intercepting an interstellar visitor had a certain romantic appeal. But ESA's budget was even tighter than NASA's, and coordinating an international mission on a 60-day timeline was politically complex. At SpaceX, the response was different. Elon Musk, who had spent years talking about making humanity a multiplanetary species, saw the intercept concept as a proof of concept for something larger, the ability to respond rapidly to unexpected events in space, whether they were scientific opportunities, asteroid threats, or, and he was careful not to say this too loudly, potential first contact scenarios. In a late-night email to his senior leadership team, Musk wrote, "If we can catch 3 Atlas, we prove we can catch anything. That's worth doing." He proposed a cost-sharing arrangement, SpaceX would provide the Starship launch at cost, NASA, or SA, would fund the probes, and a consortium of universities would handle science operations. The proposal landed on desks at NASA headquarters and SA's Director General's office within 48 hours. And then, it stalled. Not because the idea was bad, everyone agreed it was audacious and technically feasible, but because the timeline was impossible. 60 days wasn't enough time to design, build, test, and integrate a payload. Even with commercial off-the-shelf components and a streamlined approval process, it would take at least 6 months. By then, 3E Atlas would be gone. The intercept mission died quietly, relegated to a folder labeled Future Opportunities and a series of lessons learned workshops where engineers would dissect what went wrong and how to move faster next time. But the fact that it had been seriously considered, that teams at multiple agencies had run the numbers, sketched the trajectories, and concluded it was possible, marked a shift. Starship was no longer just a vehicle for ferrying cargo to the moon. It was a tool for reaching out into the dark, for responding to the unexpected, for catching things that were not supposed to be caught. And somewhere, threading its way past the orbit of Mars, 3 Atlas continued on its hyperbolic path, indifferent to the debates happening millions of miles behind it. For now, it would remain unvisited. But the engineers had done their work. The whiteboard trajectories had been drawn. And the next time an interstellar visitor passed through, the window of opportunity might not close so quickly. 3 Atlas doesn't slow down while we decide what to believe. Chapter 6, November 11, 2025. JUICE in the coma. The JUICE spacecraft, formerly known as the Jupiter Icy Moons Explorer, was launched by ESA in April 2023 with a single focused mission: travel to Jupiter and study its 3 largest icy moons, Ganymede, Callisto, and Europa, searching for signs of subsurface oceans and the conditions necessary for life. It was not designed to study comets. But space missions are expensive, and opportunities are rare, and when a once-per-civilization interstellar visitor crossed JUICE's path at a distance of just over 100 million kilometers, mission planners decided to take advantage of the phi geometry. On November 11, 2025, JUICE turned its instruments toward 3I Atlas. The observation window was short, just 6 hours, squeezed between gravitational assist maneuvers and instrument calibration activities, but it was enough. JUICE carried 10 scientific instruments, a suite of cameras, spectrometers, and magnetometers designed to probe the properties of ice, rock, and plasma around distant moons. Those same instruments, pointed at a comet, could reveal details invisible to ground-based telescopes or even Hubble. The navigation camera, or NavCam, captured the first images, wide-field, black-and-white frames showing the comet as a bright smudge against the star field, its coma clearly visible, its tail stretching across the frame like a faint brushstroke. The Janus camera, a high-resolution imager designed for surface mapping, zoomed in closer. It resolved structure within the coma, shells or concentric layers of brightness, radiating outward from the nucleus in a pattern that suggested periodic activity, jets firing in pulses rather than continuously. The MAGI spectrometer, operating in the near-infrared, began dissecting the light from the coma, breaking it into thousands of individual wavelengths, and searching for the spectral fingerprints of specific molecules. Water vapor, as expected. Lots of it. Carbon monoxide, also expected, though in slightly higher abundance than typical for comets in our solar system. Carbon dioxide, nitrogen, methane, all present, all within the range of normal variability. And then buried in the noise, something unusual. A faint emission feature at a wavelength associated with complex organic molecules, hydrocarbons, nitriles, possibly even amino acids, or their precursors. The signal was weak, just barely above the detection threshold, and it would take weeks of careful analysis to confirm. But it was there. Organics, one of the instrument scientists said, staring at the spectrum on her screen. That's not shocking. Comets are full of organics. Yes, her colleague replied, but look at the ratio. He pulled up a comparison plot, showing the spectrum of 3I Atlas next to spectra from a dozen well-studied comets in our solar system. The organics to water ratio was off. Not wildly off, but enough to be noticeable, higher than you'd expect for a comet formed in the cold outer regions of a protoplanetary disk. Could be interstellar chemistry, he suggested. Different radiation environment, different starting materials. Could be, she agreed. But there was another possibility, unspoken but hanging in the air between them. What if the organics weren't a relic of formation, but something added later? Something produced, or carried, by the nucleus itself. The Meiji team filed the data and moved on to the next observation. Meanwhile, the magnetometer onboard JUICE, an instrument designed to measure the magnetic fields around Jupiter's moons, was picking up something strange. Space is not empty. Even in the vacuum between planets, there are magnetic fields, carried by the solar wind, twisted into spirals by the sun's rotation, and disturbed by passing objects like comets. When a comet's coma, a cloud of ionized gas, interacts with the solar wind, it creates a region of turbulence, a magnetospheric boundary where the two plasmas collide and mix. That boundary is messy, full of waves and instabilities, and it's one of the most dynamic environments in the solar system. JUICE's magnetometer was recording that interaction, and it was recording something else. As the instrument swept across the region around 3 Atlas, it detected fluctuations in the magnetic field strength, oscillations, repeating at a frequency of roughly 0.1 Hz, or one cycle every 10 seconds. At first, the team thought it was an artifact, noise from the spacecraft's own systems. But the signal was too clean, too regular, and it persisted even when the spacecraft switched to a different operating mode. It's real, the magnetometer lead concluded after 3 days of analysis. The comet's plasma environment is oscillating. What's driving it? Someone asked. Could be instabilities in the boundary layer. Could be waves propagating through the coma. Could be the nucleus itself, if it's venting gas and pulses. Or, someone else ventured, it could be something internal. A rotating source. A magnetic field anchored to the nucleus, spinning with it. That would require the nucleus to be magnetized, which was unusual but not impossible. Some asteroids and comets have weak magnetic fields, remnants of their formation or traces of iron-rich materials embedded in their structure. But if the field was strong enough to shape the plasma tail, if it was interacting with the solar wind in a way that could bend and kink the tail, then it would have to be much stronger than typical, strong enough to be engineered. The thought lingered, unspoken, in the back of everyone's mind. The JUICE observations wrapped up on November 11th, just as the spacecraft reached the edge of its observing window and had to turn back toward its primary mission objectives. The data was downlinked over the following week, processed, archived, and distributed to the broader scientific community. And quietly in labs and universities around the world, teams began poring over the spectra, the magnetometer traces, the images of the layered coma, searching for patterns, testing hypotheses, trying to build a coherent picture of what 3 Atlas really was. One group focused on the organics, running chemical models to see if interstellar radiation could produce the observed ratios. Another group analyzed the magnetic oscillations, comparing them to known plasma instabilities and searching for alternative explanations. A third group studied the coma shells, measuring their spacing and trying to match them to rotation periods or outgassing cycles. Every analysis pointed in the same direction. 3A Atlas was more complex than it had any right to be. Not impossible, just precise. In a Slack channel shared by several institutions, someone posted a comment late one night. If you wanted to build a natural-looking beacon using only ice, dust, and sunlight, this is uncomfortably close to what it might look like. No one replied for several hours. And then finally, someone wrote, "That's a hell of a hypothesis." Yeah, the original poster responded. But can you rule it out? Silence. Because the truth was, they couldn't. Not yet. 3I Atlas doesn't slow down while we decide what to believe. Chapter 7. November 25, 2025. When the numbers stop behaving. Orbital mechanics is a precise science. Given the positions and velocities of a body in space, and the gravitational influences acting on it, you can predict where that body will be at any future time with remarkable accuracy. Centuries of observations, decades of spacecraft tracking, and the accumulated weight of millions of astrometric measurements have refined our models to the point where we can land a probe on a speeding comet or fly a spacecraft through the gap between Saturn's rings. But precision only matters if your assumptions are correct. On November 25, 2025, those assumptions began to crack. A new combined orbit solution for 3I Atlas dropped into the public databases, JPL's Horizon System, ESA's Minor Planet Center, and several other repositories used by researchers around the world. It folded in the latest data: Hubble astrometry, JUICE tracking, ground-based observations from Rubin, which had recently come back online after its hiatus, and radar ranging from the Deep Space Network. The solution was the most accurate yet, with uncertainty ellipses shrunk to a fraction of what they had been in July. And it revealed something no one had expected. The closest approach distance, the point where 3I Atlas would pass nearest to Earth's orbit, had shifted. Not by much, just a few million kilometers. But it was closer than earlier projections. Much closer. According to the updated ephemeris, 3E Atlas would pass within approximately 40 million kilometers of Earth's orbital path in mid-January 26, threading through the inner solar system at a point where several major observatories would have optimal viewing geometry. Not close enough to be a threat, not even close to that, but close enough to be convenient. One dynamicist, reviewing the new solution in his office late at night, pulled up a visualization tool and plotted the trajectory in 3 dimensions. He added overlays showing the positions of Earth, Mars, and the major space telescopes over time, color-coded by observation quality. The path of 3I Atlas wound through the inner solar system like a thread through a needle, slipping past Earth at a distance that maximized ground-based visibility while staying just far enough away to avoid triggering automated hazard assessments. He zoomed in, adjusted the timeline, and watched as the comet's path intersected the fields of view of Hubble, Webb, and several ground-based surveys, but only briefly, long enough to be noticed, not long enough to be thoroughly characterized. He ran a Monte Carlo simulation, generating 10,000 synthetic trajectories with similar orbital elements, randomly perturbed within the uncertainties of the initial discovery observations. Only a handful of those synthetic trajectories came as close as 3 Atlas. He tightened the constraints, requiring that the trajectories also pass through optimal viewing windows for at least 3 major observatories. The number dropped further. He added one more criterion. The trajectory had to thread through the inner solar system during a period when the most capable survey telescope, Rubin, was offline or operating at reduced capacity. The number dropped to 0. Except for 3 Atlas itself. He sat back in his chair, staring at the plot, and felt a chill that had nothing to do with the temperature in the room. The odds of an interstellar object, arriving from a random direction with a random velocity, threading this exact path by chance were low. Not impossible. Nothing in orbital mechanics is truly impossible, but low enough to be uncomfortable. He ran the numbers, roughly 1 in 20,000. 1 in 20,000. He wrote the result down, checked it twice, and emailed it to a colleague with the subject line, "Weird coincidence or something else?" The reply came back 15 minutes later. Define something else. That was the question, wasn't it? If 3I Atlas wasn't just a random visitor, if its path had been chosen or adjusted or guided in some way, what did that mean? It could mean natural processes, gravitational interactions with unseen objects in the outer solar system, perturbations from passing stars during its long journey through the galaxy, were conspiring to produce a trajectory that looked deliberate. Or it could mean something was steering. The dynamicist didn't share his results widely. Not yet. He wanted to check the data again, run more simulations, rule out as many alternative explanations as possible, before saying anything that might sound speculative or alarmist. But he couldn't shake the feeling that the numbers were trying to tell him something. That 3I Atlas wasn't just passing through. It was aiming. A week later, a risk analysis group at NASA's Planetary Defense Coordination Office ran their own Monte Carlo simulations, focused not on observability, but on collision probability. Their mandate was simple: Assess whether 3i Atlas posed any threat to Earth or Earth-orbiting assets. The answer, statistically, was no bow. The comet's closest approach would keep it well outside the Moon's orbit, and the uncertainties in the trajectory were small enough that even the worst-case scenarios didn't bring it dangerously close. But one analyst, reviewing the results, noticed the same pattern the dynamicist had seen. The trajectory was threading a very narrow corridor, one that balanced visibility against proximity in a way that seemed intentional. She flagged it in her report, adding a note in the margin. Statistical outlier. Recommend continued monitoring. Her supervisor read the note, frowned, and called her into his office. Are you suggesting this thing is being controlled? He asked. I'm suggesting, she replied carefully, that we should treat this as a low probability, high impact scenario and plan accordingly. Which means more observations, better models, and maybe, just maybe, a contingency plan in case it doesn't do what we expect. The supervisor nodded slowly. Okay, draft a memo, but keep it technical, no speculation. She did. The memo, circulated internally at NASA and shared with a few international partners, laid out the updated orbital parameters, the statistical analysis, and a recommendation for enhanced monitoring through the closest approach period. It was dry, factual, and deliberately understated. But between the lines, anyone paying attention could read the subtext. We don't know what this is, and we don't know what it's going to do, and that should concern us. On December 1st, a journalist with contacts inside the planetary science community caught wind of the memo and reached out for comment. Can you confirm that NASA is tracking an interstellar comet that might pose a risk to Earth? She asked. The reply was measured. We are monitoring 3i Atlas as part of our standard planetary defense protocols. Current data indicates no threat to Earth. But the trajectory is unusual. All interstellar objects are unusual by definition. We're gathering data and refining our models. Whoa. The journalist published a short article, carefully worded, emphasizing that there was no danger, but noting that scientists were paying unusually close attention to this particular comet. It didn't go viral. It didn't spark panic. But it added one more thread to the growing tapestry of attention surrounding 3i Atlas. And somewhere, threading its way past the orbit of Mars, the comet continued on its path, its trajectory locked into a solution that fit the data perfectly but felt, to those who studied it closely, like something that had been calculated rather than discovered. 3i Atlas doesn't slow down while we decide what to believe. Chapter 8. December 3rd, 2025. The Sky We Broke. On December 3rd, 2025, a NASA-led study appeared in the journal Nature Astronomy with a title that understated its implications: Impact of Large Satellite Constellations on Future Space Telescope Performance. The paper was dense, 40 pages of analysis, simulations, and photometric models, but its core message could be summarized in a single sentence: we are losing the night sky. Not to light pollution, though that remains a problem. Not to atmospheric interference, though that too is worsening. We are losing it to ourselves, to the tens of thousands of satellites we are launching into low Earth orbit, painting streaks across every long-exposure image, saturating sensors, and turning the pristine black of space into a crowded highway of space, into a crowded highway of glinting metal. The study focused on upcoming space telescopes, missions like the Nancy Grace Roman Space Telescope, the Habitable Worlds Observatory, and several smaller instruments designed to study everything from exoplanets to dark energy. These telescopes were designed to peer deep into the universe, stacking hours of exposure time to capture the faintest signals. But you can't stack exposures if every frame contains a satellite trail. The simulations in the paper were stark. For some observation modes, up to 96% of images could be contaminated by satellite streaks, rendering them unusable for certain types of science. Even with mitigation strategies, adjusting pointing, masking affected regions, developing software to subtract trails, the losses would be significant. One figure in the paper showed a time-lapse simulation, a deep field image built up over 10 hours with satellite trails flickering through the frame like meteors. The final composite looked less like a window into the cosmos and more like a photograph of a highway at night, streaked with headlights. The authors were careful to emphasize that this was not an anti-satellite screed. The constellations, Starlink, OneWeb, and others, provided valuable services, connecting remote regions, enabling global communications, and supporting scientific research. But there was a cost. And that cost was being paid by the very instruments designed to answer humanity's oldest questions. Are we alone? Where did we come from? What is the universe made of? The connection to 3IS was not explicit in the paper, but it didn't have to be. 3IS was exactly the kind of object that required continuous, high-cadence observations, tracking its motion, measuring its brightness, monitoring its tail structure, searching for subtle changes in activity. The kind of observations that depended on clean, uncontaminated images. And those images were becoming rarer. Rubin, with its enormous field of view, was particularly vulnerable. Every exposure captured not just the sky, but also dozens of satellite trails, each one a bright streak that had to be identified, masked, and removed from the data pipeline. The process was automated, but it wasn't perfect, and it slowed everything down. Hubble, orbiting above the densest layers of the satellite constellations, was better off. But even Hubble occasionally caught a stray trail, and the longer the constellation grew, the more frequent those intrusions would become. James Webb, positioned at the L2 Lagrange point nearly 1 million miles from Earth, was mostly immune, but its observing schedule was packed years in advance, and adding new targets required navigating a labyrinth of committees, proposals, and priorities. In short, the very instruments that should have been tracking 3I Atlas with unrelenting focus were being forced to work around an infrastructure of our own making. One astronomer, interviewed for a follow-up article about the Nature Astronomy paper, put it bluntly, "We're building the tools to explore the universe, and we're simultaneously building the barriers that prevent us from using them." In a Slack channel shared by several observatories, someone posted a link to the paper with the comment, "Great. Now we're not just racing against the comet. We're racing against our own satellites." Another replied, "At least the comet doesn't leave debris." The conversation drifted into gallows humor, a coping mechanism for scientists who had spent careers navigating budget cuts, political interference, and now, apparently, the slow encroachment of orbital infrastructure on their observing windows. But beneath the jokes, there was genuine frustration. Because the problem wasn't just technical, it was political. Regulating satellite constellations required international coordination, treaties, agreements, enforcement mechanisms, and none of that moved at the speed necessary to keep pace with commercial launch schedules. By the time regulators drafted guidelines, companies had already doubled the size of their constellations. There were proposals: darker coatings to reduce reflectivity, operational restrictions to avoid certain orbital planes, compensation funds to help observatories upgrade their instruments. But proposals take time, and 3I Atlas didn't have time. On December 6th, 3 days after the Nature Astronomy paper was published, an op-ed appeared in the New York Times under the headline, "The Sky is Not Ours Alone." The author, a veteran planetary scientist who had worked on missions to comets, asteroids, and the outer planets, argued that the satellite constellations represented a form of observational enclosure, a privatization of the commons that disproportionately benefited commercial interests, while imposing costs on scientific research. "We are at a crossroads," the op-ed read. "We can choose to preserve the night sky as a shared resource, a place of discovery and wonder, or we can allow it to become a billboard, a commodity, a background hum that we learn to ignore. But once we make that choice, there is no going back." The piece was widely shared, debated on social media, cited in congressional hearings, and promptly ignored by the companies launching the satellites. Because the incentives were clear. Global connectivity was profitable, politically popular, and technologically achievable. Deep sky astronomy was none of those things. And so the constellations grew, and the observational windows shrank. And somewhere, threading its way through that shrinking window, 3 Atlas continued on its hyperbolic path, indifferent to the human drama unfolding in its wake. The irony was not lost on the scientists tracking it. An interstellar visitor, arriving at a moment when humanity was most capable of studying it, and least able to see clearly. A message, perhaps, written in motion and obscured by our own noise. 3. Atlas doesn't slow down while we decide what to believe. Chapter 9. December 4th, 2025. Infrared eyes and solar wind vanes. While the debate over satellite constellations raged in journals and op-eds, other instruments, quieter, less visible, but no less important, continued their work. On December 4th, 2025, two of those instruments delivered data that would quietly reshape how scientists understood 3 Atlas. The first was SphereX, the spectrophotometer for the history of the universe, epoch of reionization, and ICE's Explorer. SphereX was designed to map the entire sky in infrared light, capturing spectra for hundreds of millions of objects and searching for the faint glow of water ice and organic molecules in distant star-forming regions. But SphereX could also look closer to home. On the night of December 4th, as part of its routine all-sky survey, SphereX swept across the patch of sky where 3 Atlas was crossing. The comet was faint in visible light, but in the infrared, where molecules like water vapor and carbon monoxide emit strongly, it was a beacon. The SphereX spectra, covering wavelengths from 0.75 to 5 microns, revealed a detailed chemical portrait. Water vapor, as expected, dominated the emissions. But beneath that, hidden in the spectral forest of absorption and emission lines, were signatures of other molecules: methane, ammonia, formaldehyde, and a suite of carbon-bearing species that hinted at complex chemistry in the coma. One research group, analyzing the SphereX data, noticed something unusual. The ratio of carbon monoxide to water was higher than expected for a comet formed in the outer solar system. Not impossibly high, but enough to suggest that 3 Atlas might have formed in a colder, more carbon-rich environment than typical comets. Or, alternatively, that its composition had been altered, either by prolonged exposure to interstellar radiation or by some other process. "It doesn't quite fit," one of the researchers said, staring at the spectrum. "It's like someone took a normal comet and turned up the carbon dial." "Could be interstellar," her colleague suggested. "Different stellar nursery, different chemistry." "Maybe," she replied. "But it's a big difference. Bigger than I'd expect from just changing the formation environment." They filed the observation and moved on. But the discrepancy lingered in the data, one more anomaly in a growing list. The second instrument was PUNCH, the polarimeter to unify the corona and heliosphere, a suite of 4 small satellites launched by NASA in April 2025. PUNCH was designed to study the sun's outer atmosphere, the corona and the solar wind, by imaging the faint glow of sunlight scattered by electrons and dust in space. It was, in essence, a camera for seeing the invisible. On December 4th, PUNCH captured an image of the solar wind streaming past the position of 3 Atlas, and for the first time scientists could see, in exquisite detail, how the comet's plasma tail interacted with that wind. The solar wind is not uniform. It's a turbulent, clumpy flow, full of fast streams and slow streams, magnetic field lines twisted into spirals, and shocks, where fast wind overtakes slow wind and piles up into a pressure wave. PUNCH revealed all of it, and it revealed how 3 Atlas's tail responded. The plasma tail was anchored to the coma, where ionized molecules were continuously produced by solar ultraviolet radiation. From there, the ions were picked up by the solar wind and dragged downstream, forming a long, glowing streamer. But the streamer didn't just flow passively. It kinked, twisted, and occasionally disconnected entirely, severing from the coma and drifting away like a ghost tail before a new tail formed to replace it. These disconnection events are known in comet science. They happen when the magnetic field of the solar wind changes polarity, severing the connection between the coma and the tail. They're dramatic, but predictable. Except that 3 Atlas's disconnections didn't always line up with the solar wind data. One research group, overlaying PUNCH images with solar wind measurements from spacecraft near Earth, noticed that several of the disconnection events occurred when the solar wind was steady, with no obvious trigger. "Could be local," one researcher suggested. "Instabilities in the coma itself." "Or jets," another added. If the nucleus is venting gas asymmetrically, it could create local pressure variations that sever the tail. Or, a third said quietly, it could be controlled. No one responded. Because that third option, controlled, implied something no one wanted to say out loud. Elsewhere, in a completely different context, the James Webb Space Telescope was making headlines for an unrelated discovery. Webb had been studying exoplanets, specifically a class of worlds known as superpuffs, planets with the mass of Neptune, but the size of Jupiter, so low in density that they seemed almost impossible. In early December, Webb released detailed spectra, showing that these planets were shedding their atmospheres at prodigious rates, losing helium and hydrogen in vast plumes that trailed behind them like cometary tails. The images were stunning, planets wrapped in glowing halos, their atmospheres streaming away into space, sculpted by the light and wind from their parent stars. One science journalist, writing about the discovery, included a side-by-side comparison, a superpuff planet shedding its atmosphere, and 3E, Atlas, shedding its coma. The caption read, "Everywhere we look, things are losing material to space. The way they lose it carries information." It was a poetic connection, not a scientific one. But it resonated. Because whether you were looking at a distant exoplanet or an interstellar comet, the principle was the same. Mass loss is a signature, a fingerprint, a way for an object to leave a trace of itself in the environment around it. And if that mass loss was structured, layered, pulsed, timed, it could carry information. Not necessarily a message, but not necessarily random either. On the night of December 4th, as spherics and punch data streamed into archives and Webb's exoplanet images circulated through the media, one researcher sat alone in her office, staring at a plot that combined all three datasets. Infrared spectra showing chemical anomalies. Solar wind images showing unexplained disconnections. Exoplanet halos showing structured mass loss. She didn't know what it meant, but she knew it meant something. 3I Atlas doesn't slow down while we decide what to believe. Chapter 10, December 5th, 2025. The Whisper at 1420 mH2. There's a frequency in the radio spectrum that holds a special place in the search for extraterrestrial intelligence. 1420 MHz starter. It's the frequency at which neutral hydrogen, the most abundant element in the universe, emits radiation when its electron flips from one spin state to another. The emission is weak, but it's everywhere, a background hum that pervades the galaxy, marking the presence of hydrogen clouds, star-forming regions, and the diffuse interstellar medium. And because hydrogen is so common, because any civilization with radio technology would inevitably discover this frequency, it has become known as the cosmic waterhole, a natural place to listen for signals. On December 5th, 2025, radio arrays around the world quietly pointed at 3I Atlas. Not because anyone expected to find a signal, but because it was worth checking. The observations were commensal, piggybacking on other science programs. When the Very Large Array New Mexico swept across a patch of sky near 3 and Atlas, its correlator, essentially a supercomputer that processes radio signals from dozens of antennas, recorded the data and flagged a small portion for later analysis. The same happened at LOFAR, the low-frequency array in the Netherlands, and at Meerkat, a powerful radio telescope in South Africa. Most of what they recorded was familiar, the faint radio glow of distant galaxies, pulsars ticking like cosmic clocks, the crackling static of Earth's ionosphere. But one analysis group, sifting through the data weeks later, noticed something odd. A weak, broadband modulation in the signal from the direction of 3 Atlas. It wasn't a narrowband tone, the kind you'd expect from a deliberate transmission. It was spread across several megahertz, more like noise than a signal. But it wasn't random noise. It had structure. The modulation repeated roughly every 12 hours, a slow rise and fall in intensity that seemed to correlate with the estimated rotation period of the comet's nucleus. Interesting, one of the radio astronomers said, pulling up a waterfall plot showing the signal strength over time. But probably nothing. Probably, her colleague agreed. Could be interference, could be scintillation from the solar wind, could be a data processing artifact. Could be the comet itself, she suggested. If the nucleus is venting gas asymmetrically, And if that gas is ionized, it might emit radio waves as it interacts with the solar wind. That's a lot of ifs. True. They ran a series of tests, comparing the signal to known sources of radio frequency interference: satellites, ground-based transmitters, radar systems. None matched. They checked the solar wind data, looking for bursts of activity that might have caused scintillation. There were a few, but the timing didn't line up with the modulation. They ran a statistical analysis, calculating the probability that a random noise source would produce this particular pattern by chance. The result: about 5%. Not low enough to claim a detection, but not high enough to dismiss it entirely. "We can't prove it's real," the first astronomer said finally. "But we can't prove it's not. So what do? We report it. Carefully. And we ask for more observing time." They drafted a short paper, just 3 pages, describing the observation and outlining possible explanations. They emphasized that the signal was weak, that alternative explanations existed, and that further observations were needed to confirm or refute the finding. The paper was submitted to a journal specializing in radio astronomy, where it would undergo peer review and, if accepted, be published months later. But in the meantime, they shared the preprint on the arXiv, the public repository where most astronomers post their work before formal publication. And within hours, someone noticed. A SETI researcher, scrolling through the latest arXiv postings, saw the title, "Possible Radio Modulation from 3i Atlas," and clicked. She read the paper twice. Then she opened a Slack channel and pinged her team. "You need to see this." The SETI Institute, based in California, has been searching for signals from extraterrestrial civilizations for decades. Their telescopes, most notably the Allen Telescope Array, scan the sky continuously, listening for narrowband signals, repeating patterns, anything that might indicate the presence of technology. They had been tracking 3i Atlas since July, not because they expected it to be artificial, but because it was an unusual object, and unusual objects are worth checking. So far, they had found nothing. But the arXiv preprint changed that. If the radio modulation was real, if it was tied to the comet's rotation, and if there was any chance, however small, that it was intentional, then 3 Atlas had just become one of the most important targets in the sky. Within 24 hours, the Allen Telescope Array was retasked. It pointed at 3 Atlas and began recording. The observations ran for 3 nights, covering a full rotation cycle of the nucleus. The data was processed in near real time, fed through algorithms designed to detect narrowband signals, broadband pulses, and structured modulations. Most of the time, the signal was noise. But twice, once on the first night, once on the third, the algorithm flagged a weak modulation, similar to what had been reported in the arXiv preprint. It was faint. It was at the edge of detectability. It was not a smoking gun. But it was there. The SETI team held an internal meeting to discuss how to interpret the result. "It's not a technosignature," one researcher argued. "Technosignatures are narrowband, coherent, clearly artificial. This is just noise with a pattern." "But what if that's the point?" another replied. "What if you wanted to send a signal that looked natural? You wouldn't use a narrowband tone. You'd modulate something that's already there. The radio emissions from the coma, the solar wind interaction, and you do it subtly, so it blends in." "That's a hell of an assumption." "I know, but can we rule it out?" The question hung in the air, unanswered. Because the truth was, they couldn't rule it out. Not with the data they had. Not without more observations, more analysis, more time. And time was running out. On December 8th, 3 days after the SETI observations concluded, a press release was issued, not by SETI, but by the radio astronomy group that had published the original preprint. The release was carefully worded. "Continued monitoring of 3i Atlas has detected a weak periodic modulation in radio emissions that may be associated with the comet's rotation. While natural explanations are favored, the signal warrants further investigation." No mention of SETI. No mention of technosignatures. No mention of the possibility that someone, or something, might be trying to communicate. But the message was clear. We are listening, and we are hearing something. Whether it's a whisper from the void or just the wind between the stars, we don't yet know. But we are listening. 3i Atlas doesn't slow down while we decide what to believe. Chapter 11, December 6, 2025. The warning hidden in its latest trajectory update. There is a particular kind of document in planetary science that most people will never see. It's called an ephemeris, a table of numbers listing where an object will be at specific times, calculated from its orbit and projected forward or backward in time. Ephemerides are dry, technical, dense with coordinate systems and reference frames, and they are the backbone of every space mission, every observation campaign, every attempt to point a telescope or spacecraft at something moving through the dark. On December 6, 2025, the latest ephemeris for 3i Atlas was released. It was version 12 Torfshade. The previous version, released 3 weeks earlier, had been based on data through mid-November. Version 12 incorporated everything since then. Rubin's resumed observations, Hubble's latest tracking, radar ranging from the Deep Space Network, and JUICE's close encounter data. The uncertainties were smaller than ever. The orbital elements were pinned down to 5 significant figures. The trajectory was as well determined as it was ever going to be. And when one researcher plotted it against the observing schedules of the world's major telescopes, something strange emerged. He worked late into the night, alone in his office, a cup of cold coffee sitting untouched on his desk. He had been building this plot for weeks, adding layers, ephemerides, telescope schedules, satellite orbital data, weather forecasts, funding timelines, trying to visualize the full picture of how humanity would observe 3 Atlas over the coming months. The plot was a mess of overlapping colors and annotations, but a pattern was starting to emerge. Atlas's path threaded through the inner solar system in a way that maximized brief visibility while minimizing long, continuous observing windows. It passed through Rubin's field of view during the September engineering hiatus when the telescope was offline. It crossed through Hubble's optimal viewing zone during a period when the telescope was committed to other high-priority targets. It reached its brightest phase just as the densest layers of satellite constellations passed overhead, contaminating ground-based observations. It swung past Earth, at a distance that was close enough to be noticeable, but far enough to avoid triggering automated hazard assessments or emergency response protocols. And it did all of this during a fiscal year when NASA's planetary science budget was under pressure. ESA's missions were overcommitted, and no rapid response intercept mission could be funded or launched in time. Individually, each of these coincidences could be explained. But together, he leaned back in his chair and stared at the plot. The odds, according to his Monte Carlo simulations, were about 1 in 20,000. 1 in 20,000. Not impossible. Just unlikely. He saved the plot, exported the data, and wrote an email to a small group of colleagues, dynamicists, mission planners, a few senior scientists he trusted. The subject line read, 3A Atlas, Observational Geometry Analysis. The body of the email was brief. I've been looking at the trajectory in the context of our observing infrastructure. Attached is a plot showing the comet's path overlaid with telescope schedules, satellite constellations, and budget timelines. I'm not claiming anything, but I think we should discuss this. Well, no. He hit send and went home. By the next morning, his inbox had exploded. Some responses were skeptical. You're reading too much into it. Coincidences happen. Others were intrigued. This is worth a closer look. Can you share your simulation code? And a few were blunt. If you're suggesting this thing is being steered, you need to say so explicitly. Otherwise, you're just spreading FUD. But no one could dismiss it outright. Because the data was solid, the analysis was rigorous, and the pattern was undeniable. 3i Atlas was threading the needle. On December 10th, a virtual meeting was convened. Scientists from NASA, ESA, several universities, and a few private aerospace companies. The agenda was simple: review the latest trajectory data and assess whether 3i Atlas warranted any special attention. The dynamicist who had created the plot presented first. He walked through the ephemeris, the Monte Carlo simulations, the observing geometry analysis. He showed how the comet's path intersected the gaps in humanity's observational infrastructure with uncomfortable precision. I'm not saying it's being controlled, he concluded. I'm saying the odds are low enough that we should treat this as a statistical outlier and plan accordingly. There was silence on the call. Then someone asked the question everyone was thinking. If it is being controlled, what does that imply? The dynamicist hesitated. It implies that something chose this path. And if something chose this path, it chose it for a reason. What reason? I don't know. Maybe it's trying to avoid close scrutiny. Maybe it's trying to be noticed but not fully characterized. Maybe it's just passing through, and we're the ones reading intent into random chance. Nay. Or maybe, someone else said quietly, it's trying to tell us something, and we're too busy arguing about statistics to listen. The meeting ran long, circling through the same arguments, the same uncertainties, the same reluctance to commit to any definitive conclusion. In the end, they agreed on a few things. 3. Atlas should remain a high-priority target for all available observatories. The trajectory should be reanalyzed continuously as new data came in, with particular attention to any deviations from the predicted path. A small contingency fund should be set aside to support rapid response observations if the comet exhibited any unexpected behavior. And, though no one said it explicitly, everyone on the call understood that they were entering uncharted territory. Because whether 3E Atlas was natural or not, its path was forcing humanity to confront a question it had been avoiding for decades. What do we do when we encounter something we don't understand, and we don't have time to figure it out? Later that night, one of the participants in the meeting posted a comment in a shared Slack channel. I keep thinking about Oumuamua. We saw it, we tracked it, we watched it leave, and we still don't know what it was. With 3I Atlas, we have more data, better instruments, more time. But I'm starting to think that won't be enough. Nanter. Someone replied, why not? Because the original poster wrote, I think the warning isn't in what the comet is. It's in how we respond to it. What do you mean? I mean, this is a test, not from the comet, from us, and I don't think we're passing. No one responded after that, because deep down, everyone knew it was true. 3 Atlas was revealing something about humanity, about our infrastructure, our priorities, our ability, or inability, to respond to the unexpected. And whether the comet was intentional or not, the warning was real. We are not ready. 3. Atlas doesn't slow down while we decide what to believe. Chapter 12. December 7th, 2025. The meeting behind closed doors. Not every meeting makes it into the public record. Some are documented in meticulous minutes, every word transcribed and archived for future historians. Others are recorded only in personal notes, scribbled on margins and forgotten in file drawers. And a few, the most important few, are remembered only by those who were in the room. On December 7th, 2025, one such meeting took place. It was held remotely over a secure video conference link, with participants dialing in from NASA headquarters in Washington, ESA's Operations Center in Darmstadt, the Jet Propulsion Laboratory in California, and a handful of undisclosed locations. The attendees included mission scientists, budget directors, a few senior administrators, and, notably, 2 representatives from the Office of Planetary Defense. The agenda, circulated 24 hours in advance, had a single line: 3 Atlas, status, and recommendations. The meeting began with a presentation from the lead dynamicist, the same researcher who had created the observational geometry plot. He walked through the latest trajectory data, the statistical analysis, and the growing list of anomalies, the non-gravitational forces, the plasma tail kinks, the radio modulation, the eerily precise path through our observational windows. He did not speculate. He did not editorialize. He simply laid out the facts. When he finished, there was a long pause. Then one of the administrators spoke. So what are you saying? That this thing is artificial? I'm saying, the dynamicist replied carefully, that we can't rule it out. But you also can't prove it. Correct. So where does that leave us? Another pause. One of the planetary defense representatives jumped in. It leaves us with a decision. We can treat this as a purely scientific curiosity, continue observations, publish papers, Or we can treat it as a potential anomaly, classify some of the data, coordinate with international partners, and prepare a more comprehensive response. One today will do milch to get into the buy at home. Classify? Someone asked. On what grounds? National security. If there's any chance, that 3 Atlas is a probe, a reconnaissance mission, or any form of directed object, that falls under our mandate. And if it's just a comet? Then we declassify it later, apologize for the overreaction, and everyone moves on. But if it's not just a comet, and we didn't take precautions, we'll have a much bigger problem. The planetary defense argument carried weight. The office had been established specifically to coordinate responses to potential asteroid impacts, but its mandate had quietly expanded over the years to include unidentified objects exhibiting anomalous behavior. Oumuamua had tested that mandate back in 2017, sparking internal debates about whether an interstellar object could be classified as a security concern. In the end, the decision had been made not to classify. Oumuamua was too far away, too poorly characterized, and already leaving. But 3I Atlas was different. It was closer. It was better studied. And its trajectory looked, to those who examined it closely, less like chance and more like choice. The meeting shifted to a discussion of logistics. If they decided to classify some of the data, what would that mean? Would observatories be required to submit their observations to a central clearinghouse before making them public? Would international partners be brought into the loop or kept in the dark? And most importantly, what would they tell the public? One of the ESA representatives spoke up. We need to be very careful here. If we classify data without clear justification, we'll spark exactly the kind of speculation we're trying to avoid. People will assume we're hiding something, and they won't be entirely wrong. But if we don't classify, the planetary defense rep countered, and this turns out to be something significant, we'll have lost our window to coordinate a response. What kind of response are we talking about? Someone asked. That depends. If it's a probe, we might want to attempt communication. If it's a derelict, we might want to intercept and study it. If it's something else entirely, we'll cross that bridge when we come to it. The conversation turned to budgets. NASA was already stretched thin, juggling commitments to Artemis, Mars sample return, and a dozen smaller missions. Adding a high-priority, rapid response project to the docket would require either cutting something else or requesting emergency supplemental funding from Congress. ESA was in a similar position, with limited discretionary funds and a politically complex process for reallocating resources. And SpaceX, the only entity with the launch capability to mount a rapid intercept, had already indicated they would participate, but only if someone else paid for the payload. So we're back to the same problem, one of the budget directors said. We don't have the money, we don't have the time, and we don't have consensus on whether this is even worth pursuing. But what if it is? Someone asked. What if this is the moment, the one time in human history when something reaches out or passes by, or tries to communicate, and we miss it because we couldn't get our act together? Silence. Because that was the real question. Not, is 3I Atlas artificial? But, what do we do if it is, and we're not ready? The meeting concluded without a formal decision. Instead, the group agreed to reconvene in a week, after more data had been gathered, and after a few key individuals, including the NASA administrator and ESA's director general, had been briefed. In the meantime, observations would continue. The data would remain public, and the world would keep watching, unaware of the debate happening behind closed doors. But one thing had changed. 3I Atlas was no longer just a comet. It was a test. A test of our infrastructure, our priorities, our ability to respond to the unexpected. And the grade, so far, was incomplete. After the meeting ended, one of the participants, an astronomer who had spent 30 years studying comets, stayed on the line, staring at the blank screen where the video feeds had been. She thought about all the comets she had tracked over the years. Hale-Bopp, Hecate, Lovejoy, Ison. She thought about the nights spent at telescopes, the data pipelines, the models, the papers. And she thought about how none of it had prepared her for this moment. Because whether 3i Atlas was natural or not, it was revealing something uncomfortable. That our ability to listen, to the sky, to each other, to the possibility that we might not be alone, was fragile, contingent, and always on a timer. She closed her laptop and went to bed. But she didn't sleep. 3i Atlas doesn't slow down while we decide what to believe. Chapter 13. December 8th, 2025. The Pattern and the Mirror. On December 8th, 2025, a graduate student at a university in Germany sat alone in a computer lab, staring at a three-dimensional visualization she had been building for the past 2 weeks. The visualization combined every major dataset related to 3i Atlas: Rubin's photometric tracking, Hubble's high-resolution imaging, JUICE's in-situ measurements, SpherX's infrared spectra, Punch's solar wind maps, radio observations from the VLA and about LOFAR, and the latest ephemeris data folded into a single, coherent timeline. It was the most complete picture of the comet anyone had assembled, and it was unsettling. She rotated the visualization slowly, watching the trajectory wind through the inner solar system, the plasma tail streaming behind it, the coma pulsing with jets and shells, the faint radio modulation flickering in sync with the rotation period. Each element, taken alone, had a plausible natural explanation. The non-gravitational forces? Asymmetric outgassing. The plasma tail kinks? Solar wind turbulence. The radio modulation? Ionized gas interacting with the magnetic field. The precise trajectory? Coincidence. But when you stack them all together, when you watch them play out in synchronized time, the cumulative effect was something else entirely. It looked orchestrated, not in the sense of obvious artificiality, no radio beacons, no geometric patterns, no glowing lights spelling out messages in alien script, but orchestrated in the sense that everything fit too well, aligned too precisely, timed too perfectly. The grad student paused the visualization and leaned back in her chair. She had spent the last year studying comets, learning the physics of outgassing, the dynamics of plasma interactions, the statistics of orbital mechanics. She knew the data. She understood the models. And she could not shake the feeling that she was looking at something that was both natural and intentional. A message written in the language of physics, designed to be noticed by anyone who cared to look closely enough. She exported the visualization and uploaded it to a shared repository, adding a brief note. Full timeline of 3i Atlas observations. Includes all major datasets. Worth a look. Within hours, the file had been downloaded dozens of times. Within days, it was being discussed in research groups, Slack channels, and informal meetings at observatories around the world. And within a week, it had become the closest thing the scientific community had to a consensus view. 3i Atlas was probably natural, but something about it felt deliberate. One research group, analyzing the visualization, noticed that the timing of the plasma tail kinks correlated not just with the comet's rotation, but with periods when it was passing through regions of enhanced solar wind density, natural barriers that any object trying to optimize its visibility would want to interact with. Another group, studying the radio modulation, found that the frequency structure, while too broad to be a narrow-band signal, was remarkably free of the kind of noise you'd expect from a purely chaotic process. It was, one researcher noted, suspiciously clean. And yet another group, focusing on the trajectory, ran a new set of simulations testing whether our comet could naturally acquire such a precise path through gravitational interactions alone. The answer was yes, but only if it had passed through a very specific configuration of stellar encounters over the past few million years. The probability of that configuration occurring by chance, roughly 1 in 50,000. We keep coming back to the same answer, one researcher said during a video call. It's possible, but unlikely. And the more data we get, the more unlikely it seems. So what's the alternative? Someone asked. The alternative, another replied, is that this isn't random. That something, natural or otherwise, has been shaping this comet's path for a very long time. But to what end? Silence. Because no one had an answer to that. On the night of December 8th, as the grad students' visualization circulated through the scientific community, another event occurred. An amateur astronomer in Australia, using a small telescope, and a CCD camera captured an image of 3I Atlas just as it passed in front of a distant galaxy. The comet was a faint smudge, barely visible, but the galaxy behind it, a spiral nearly 1 billion light-years away, was sharp and clear. The juxtaposition was striking, a traveler from the dark, superimposed against a structure older than our solar system, two threads of cosmic history intersecting for a brief moment. The amateur astronomer posted the image to an online forum with the caption, 3 Atlas and a distant galaxy. Thought you might like this. The image was shared thousands of times. It appeared on social media, in news articles, in blog posts about the comet. And it became, for many people, the emotional center of the 3I Atlas story, a reminder that even as we debated statistics and argued about trajectories and wondered whether this object was natural or artificial, it was still, fundamentally, a messenger d'eau, a piece of the universe, passing through, carrying information, whether intentional or not, and reflecting back to us something about who we are and what we choose to notice. One science writer, reflecting on the image, wrote, "We spend so much time trying to determine whether 3I Atlas is a comet or a probe that we forget the simplest truth. It's a mirror. It's showing us our own infrastructure, our own priorities, our own blind spots." And maybe that's the most important message of all. The article didn't go viral. It wasn't shared widely. But it was read by a few of the scientists tracking the comet, and it resonated. Because the truth was, whether 3 Atlas was natural or not, it had already accomplished something remarkable. It had forced humanity to look up, to coordinate, to question, to wonder. It had revealed the gaps in our observational infrastructure, the limits of our budgets, the fragility of our ability to respond to the unexpected. And it had reminded us that the universe is not static, not empty, not indifferent. Things pass through. Things arrive. Things change. And sometimes, if we're paying attention, we catch a glimpse of something that matters. On the night of December 8th, the grad student closed her laptop and walked outside. The sky over her city was washed out by light pollution, the stars reduced to a faint glow, barely visible. But she knew, somewhere up there, beyond the glare, 3I Atlas was threading its way through the dark. And whether or not it was trying to tell us something, it had already spoken. The question was whether we were listening. 3 Atlas doesn't slow down while we decide what to believe. Chapter 14, December 9th, 2025, after the comet, before the answer. It is the night of December 9th, 2025. And somewhere above you, threading its way past the orbit of Mars, 3 Atlas is fading. Its coma, once bright enough to be captured by amateur telescopes, is dimming as the comet recedes from the sun, the jets slowing, the ice refreezing, the tail thinning into a faint streamer that will, in a matter of weeks, dissolve entirely into the background of space. It is still there, but it is already becoming invisible. By January, it will be too faint for most ground-based telescopes. By February, only the largest instruments, Hubble, Webb, and a few specialized radio arrays, will still be able to track it. By March, it will slip beyond the orbit of Jupiter, its brightness dropping below the threshold of even the most sensitive detectors. And by mid-2026, it will cross the heliopause, the boundary where the sun's influence ends and the interstellar medium begins, and vanish into the dark from which it came. That is the trajectory. That is the path. And there is nothing anyone can do to change it. The intercept missions were never funded. The follow-up observations will happen, but they will be sparse, fragmentary, hindered by budget constraints and satellite streaks, and the simple fact that 3 Atlas is moving too fast and too far for us to keep up. And so, in a very real sense, the story of 3I Atlas is already over. But the questions remain. This episode was recorded over the past 2 weeks, during a window when the comet was still bright enough, still close enough, still observable enough to justify the attention. By the time you're hearing this, that window has already narrowed. And by the time the final data is processed, the final papers are published, the final debates are held, 3I Atlas will be a memory, a line on a plot, a name in a catalog, a footnote in the history of interstellar visitors. Unless we decide it means something more. Over the past few weeks, As this episode was being researched and written, something unexpected happened. People started paying attention. Not just scientists, though they were there, of course, running simulations, refining models, debating the implications, but everyone else too. Comments started appearing in online forums. Where can I see it? What telescope should I use? Is it really leaving forever? Amateur astronomers posted images, faint smudges against star fields, long exposure captures taken from backyards and rooftops, grainy but unmistakable. Teachers brought it into their classrooms. This is happening right now. This is what science looks like in real time. And then a few people, just a few, scattered around the world, sent messages saying they had gone outside, looked up, and felt something they couldn't quite name. Not awe, exactly. Not fear. But a kind of quiet recognition that the universe is not empty, that things pass through, and that sometimes, if we're lucky, we get to witness them. One message, sent late at night from someone in Norway, read, "I don't know if 3i Atlas is natural or artificial, but I know it made me think about how much we're not seeing, how much is happening out there that we'll never know about because we're too busy, too distracted, too focused on the ground beneath our feet. Maybe that's the real warning. Not that something is out there, but that we've stopped looking." It's a fair point. Because whether 3i is a comet or a probe, whether its trajectory is coincidence or choreography, whether its plasma tail kinks or physics or intention, none of that changes the fact that we almost missed it. It was discovered by an automated survey, flagged by an algorithm, and tracked by a network of telescopes that are underfunded, overworked, and increasingly hindered by the infrastructure we're building around ourselves. And if we almost missed this, an object bright enough to be seen by amateur telescopes, close enough to be tracked by spacecraft, strange enough to warrant international attention, what else are we missing? What else is passing through unnoticed? Because we're not looking. Or because we're looking, but the sky is too crowded to see? This is not science fiction. This is December 2025 dark. This is the world we built. And 3i Atlas is the mirror we didn't ask for. In the weeks since the latest trajectory update was released, the debate over what 3 Atlas means has quieted. Not because anyone has reached a conclusion, but because the conclusion doesn't matter as much as we thought it would. Whether the comet is natural or artificial, it has already done its work. It has revealed the gaps in our observational networks. It has highlighted the fragility of our ability to respond to the unexpected. It has forced us to confront the question, what do we do when something arrives that we don't understand, and we don't have time to figure it out? And it has reminded us that listening, really listening to the sky, to each other, to the possibility that we might be missing something important, is harder than it sounds. Because listening requires attention, and attention requires time. And time, as 3IS has made painfully clear, is always running out. So here's the final question, the one this episode was always building toward. What do we do next? Do we treat 3 Atlas as a one-off, a statistical outlier, a fascinating anomaly that will be studied in papers for the next decade, but ultimately filed away as probably natural? Further observations inconclusive? Or do we treat it as a warning? Not a warning from the comet, though that's possible, but a warning from ourselves to ourselves about what happens when we stop paying attention. Because the next interstellar visitor might not be as accommodating as 3 Atlas. It might not pass through our densest observational windows. It might not brighten at just the right time. It might not give us months of advance notice. And if we're not ready, if our telescopes are offline, our budgets are strained, our satellites are cluttering the sky, our coordination is fragmented, then we won't just miss the data. We'll miss the moment. And moments like this don't come back. On the night of December 9th, 2025, 3 Atlas is fading. But the questions it raised are not. And the choice it represents, the choice between looking away and leaning in, between complacency and curiosity, between accepting coincidence and demanding answers, is still ours to make. Before we end, one more thing. Throughout this episode, you've heard the refrain. 3 Atlas doesn't slow down while we decide what to believe. It's a reminder that the universe operates on its own timeline, indifferent to our debates, our budgets, our politics. But it's also a challenge, because if the universe isn't going to slow down for us, then we have to speed up. We have to build better instruments. We have to fund more missions. We have to coordinate more effectively, communicate more clearly, and above all, we have to keep looking up. Even when it's hard. Even when the answer isn't obvious. Even when the sky is crowded and the data is incomplete, and the path forward is uncertain. Because the alternative, ignoring the signals, dismissing the anomalies, letting the visitors pass unnoticed, is not neutrality. It's a choice. And it's the wrong one. So here's what I'm asking you to do. Hit like, subscribe, share this episode with someone who needs to hear it, and then go outside. Find a dark patch of sky, if you can. Look up and listen, not for an answer, but for the question. Because the sky is speaking. It's been speaking all along. And whether 3I Atlas was a comet, a probe, a messenger, or just a wanderer passing through, it has already told us the most important thing we need to know. We are not ready, but we could be. This is not science fiction. This is December 2025. And the story of 3 Atlas is not over. It's just beginning. Because the real warning wasn't hidden in the trajectory update. It was hidden in what we did and didn't do when we saw it. And that warning will outlast the comet, outlast this episode, outlast all of us. Unless we choose to listen, unless we choose to act, unless we choose to look up. The sky is speaking. Our job is to listen. 3I Atlas doesn't slow down while we decide what to believe. But maybe, just maybe, we can learn to believe a little faster.